12.3 Examples of rigid objects in static equilibrium. The outline of this video is as follows. First, we will clarify the important distinction between the center of gravity and the center of mass. We will follow that with a quick quiz to check our understanding of static balance. Next, we will introduce a general problem-solving strategy for objects in equilibrium. To put this strategy into practice, we will then work through 3 detailed examples: a classic seesaw problem, the case of a leaning ladder, and finally, the forces involved when a wheel negotiates a curb. Let us distinguish between 2 crucial concepts: the center of mass and the center of gravity. While they are often used interchangeably, they have distinct physical definitions. The center of mass is a geometric property representing the average position of an object's mass. As the first equation shows, its x-coordinate, x sub cm, is found by summing the product of each mass and its position, and then dividing by the total mass. The center of gravity, on the other hand, is the point where the total gravitational force on an object can be considered to act. We use this point to calculate the total torque due to weight. The torque equation shows that the total weight times the center of gravity position equals the sum of the individual weights times their positions. Now here is the key insight. If we assume the gravitational acceleration, g, is uniform everywhere on the object, then g is a constant that cancels out from both sides of the torque equations. This simplification makes the formula for the center of gravity's position identical to the formula for the center of mass. Therefore, when gravity is uniform, the center of gravity and the center of mass are the same point. Let us apply our understanding of static equilibrium to solve this quiz question. The core idea is that for the meter stick to be balanced, the clockwise and counterclockwise torques about the pivot point must be equal in magnitude. First, we identify our pivot, which is the string at the 25 centimeter mark. Next, we identify the 2 forces creating torques. The 0.50 kilogram object, located at the 0 centimeter mark, creates a counterclockwise torque. The weight of the meter stick itself creates a clockwise torque. Since the meter stick is uniform, its entire weight acts at its center of mass, which is at the 50 centimeter mark. The lever arm for the hanging object is the distance from 0 to 25, which is 25 centimeters. The lever arm for the meter stick is the distance from its center of mass to the pivot, which is 50 minus 25, also 25 centimeters. Because the system is in equilibrium, the torque from the object must balance the torque from the stick. Since torque is force times lever arm, and both the gravitational acceleration and the lever arms are the same on both sides of the equation, the masses must also be equal. Therefore, the mass of the meter stick must be 0.50 kilograms. To solve problems involving objects in static equilibrium, we use a reliable 4-step strategy. This structured approach helps ensure we account for all forces and conditions. First, we conceptualize the problem by identifying every external force acting on the object. Then, we categorize the situation by confirming that the object's translational and angular accelerations are both 0. The third step is the analysis. Here, you draw a force diagram and then apply the 2 conditions for equilibrium. Setting the net force to 0 and the net torque to 0 gives you a system of equations to solve for your unknowns. A common pitfall is forgetting a force, like friction on a ladder, or choosing an unnecessarily difficult axis for the torque calculation. Finally, you finalize your work by checking if the results make physical sense. Do the units and signs of your answers seem correct based on your diagram? Following this 4-step process methodically is the key to correctly solving any static equilibrium problem. Let us apply the first condition of static equilibrium to a classic physics problem: a balanced seesaw. Our goal in this first part is to find the upward force exerted by the support, which is also called the fulcrum. The problem states that the system is at rest, so the net force on the seesaw board must be zero. We can analyze the vertical forces to solve for the unknown support force, EAN. There are three forces acting downward: the weight of the father, which is Mf times g, the weight of the daughter, Md times g, and the weight of the uniform board itself, M times g. The only upward force is the normal force, N, from the fulcrum. Defining the upward direction as positive, we can write our equilibrium equation. The sum of the forces in the y direction equals 0. This gives us N minus the three downward weights equals 0. For this force calculation, notice that it does not matter where the father and daughter are sitting. Solving for N, we find that the upward support force must exactly balance the total weight of the board and the people on it. Now we will find the father's position, D, needed to balance the seesaw. This requires the second condition of static equilibrium. The net torque about any point must be zero. Torque is a rotational force, equal to the force multiplied by its lever arm. We strategically choose our axis of rotation to be the fulcrum. This is a smart choice, because the normal force and the board's weight both act at this point. Since their lever arms are zero, they produce zero torque, which simplifies our equation. This leaves only two torques to consider. The father's weight causes a positive, counterclockwise torque, while the daughter's weight causes a negative clockwise torque. The father's torque is his weight, M, sub F times G times his distance D. The daughter's is her weight, M, sub D times G times her distance L over 2. Setting the sum of these two torques to 0, and solving for D, gives us the final expression for the father's balancing position. Let us apply our understanding of static equilibrium to a common engineering problem involving a supported beam. The setup consists of a uniform horizontal beam, which is 8 meters long and weighs 200 newtons. One end is attached to a wall by a pin connection, which is a type of pivot that can exert both horizontal and vertical forces. The far end of the beam is supported by a cable that pulls at an angle of 53 degrees relative to the beam. Adding to the load, a person weighing 600 newtons is standing on the beam at a distance of 2 meters from the wall. Our goal is to determine the two unknown forces keeping the system in balance: the tension in the cable and the magnitude and direction of the reaction force from the wall's pin connection. We will solve for these unknowns by applying the conditions that the net force and net torque on the beam must both be 0. To find the tension, we will now apply the second condition of equilibrium, which states that the net torque on the beam must be 0. The key to this step is choosing a convenient axis of rotation to simplify our calculation. We will choose the pin connection at the wall as our axis. This is a strategic choice, because the reaction force from the wall, R, acts at this point. Since the lever arm for R is 0, it produces no torque, and this unknown force conveniently disappears from our torque equation. Now we identify the remaining torques. The vertical component of the tension, T sine phi, creates a counterclockwise torque. The weight of the person and the weight of the beam both create clockwise torques. For equilibrium, the net torque is 0. The counterclockwise torque from the cable must balance the clockwise torques from the two weights. This gives us the equation shown on the slide. Because we chose our axis wisely, this equation has only one unknown, the tension, T. We can now rearrange the formula and substitute the known values to solve for T, which gives a result of 313 newtons. By setting the sum of torques about the pin to 0, we successfully isolated and solved for the tension in the cable. Now that we have the tension, we can find the reaction force from the wall by applying the first condition for equilibrium. The net force on the beam must be 0. We do this by summing the force components in the x and y directions independently. For the x components, the outward horizontal force from the wall, r times cosine theta, must balance the inward horizontal component of the tension. For the y components, the upward forces from the wall and the cable must together balance the downward weights of the person and the beam. This gives us two equations with two unknowns, the magnitude r and the angle theta. A good strategy is to find the angle first, by dividing the y component equation by the x component equation. The magnitude r cancels out, leaving an expression for the tangent of theta. This gives us an angle of 71.1 degrees. With the angle known, we can substitute it back into the x component equation to solve for the magnitude r. This calculation shows the reaction force has a magnitude of 581 newtons. Therefore, applying the zero net force condition allowed us to find both the magnitude and direction of the wall's reaction force. We will now analyze a classic static equilibrium problem involving a leaning ladder. The setup involves a uniform ladder of mass, m, and length L, resting against a perfectly smooth vertical wall. The term, smooth wall, is an important simplification. It means we can ignore any friction at the point of contact with the wall. The only force the wall exerts is a normal force, perpendicular to its surface. The ground, however, is not smooth. It provides both an upward normal force and a horizontal static friction force that prevents the base of the ladder from sliding. We are given the coefficient of static friction for this surface as 0.40. Our objective is to find the minimum angle the ladder can make with the ground before it begins to slip. This minimum angle corresponds to the exact point where the static friction force reaches its maximum possible value. Essentially, we are finding the boundary between the ladder being stable and it slipping away. To solve for the forces on the ladder, we apply the two conditions for static equilibrium. First, the net force must be zero. In the horizontal x direction, the static friction force from the floor, Fs, balances the normal force from the wall, P. Therefore, Fs equals P. In the vertical y direction, the normal force from the ground, N, must support the ladder's weight, mg. So, N equals mg. Next, the net torque must be zero. We can strategically choose our axis of rotation to be at the base of the ladder, point O. This choice is useful because the normal force N and friction force Fs both act at this point, giving them a zero lever arm, and thus zero torque. The normal force from the wall, P, creates a positive counterclockwise torque. The weight, mg, acts at the ladder's center and creates a negative clockwise torque. Setting the sum of these torques to zero gives us our third and final equation for analyzing the system. Now let us use our equilibrium equations to find the specific minimum angle where the ladder is just about to slip. This critical point occurs when the force of static friction reaches its maximum possible values. From our torque analysis, we found a general relationship for any stable angle. The tangent of theta equals the ladder's weight, mg, divided by twice the force from the wall, P. To find the minimum angle, we use the condition for impending motion. At this point, the wall force P must balance the maximum static friction, which is the coefficient mu sub s times the normal force. Since the normal force equals the ladder's weight, P becomes mu sub s times mg. Substituting this expression for P into our torque equation reveals something interesting. The term for the ladder's weight, mg, appears in both the numerator and the denominator, so it cancels out completely. This leaves a simple result. The tangent of the minimum angle is 1 divided by the quantity 2 times mu sub s. Plugging in the given coefficient of 0.40, we find the minimum angle is 51 degrees. The important takeaway is that the minimum angle depends only on the coefficient of friction, not on the mass or length of the ladder. Let us now analyze a more common scenario for getting over a curb, where the horizontal push is applied directly at the wheel's axle. Our goal is to find the minimum force needed to just begin lifting the wheel. We will solve this by balancing the torques acting on the wheel at the moment it starts to pivot. A very powerful technique in static equilibrium problems is to choose a clever axis of rotation. Here, we will place our axis at the sharp corner of the curb. The reason this is so helpful is that the reaction force from the curb acts at this point. By putting our axis there, the moment arm for the reaction force is 0, meaning its torque is also 0. This simplifies the problem immensely, as we only need to balance the torques from our applied force and from the force of gravity. We will use the same physical parameters as before: a wheel radius of 30 centimeters, a curb height of 10 centimeters, and a total weight of 700 newtons. By choosing the curb corner as our axis, we can find the required force by focusing only on the torques from our push and from gravity. To find the minimum force needed to get over the curb, we apply the second condition for static equilibrium, which states that the net torque about any point must be 0. We choose our pivot point to be A, where the wheel contacts the curb. This is a strategic choice because the force from the curb acts at this point, creating 0 torque and simplifying our equation. The two remaining torques must balance each other. The downward force of gravity creates a counterclockwise torque, while the applied horizontal force at the top of the wheel creates a clockwise torque. From geometry, the moment arm for gravity is the square root of the quantity 2 times r times h minus h squared. The moment arm for the applied force is the vertical distance 2 times r minus h. Setting the counterclockwise torque equal to the clockwise torque and solving for F gives us the final expression. Plugging in the given values, we calculate that the required force is about 313 newtons. This analysis shows how balancing torques allows us to calculate the forces in a static system. Let us summarize the essential concepts for static equilibrium and highlight the most important problem-solving strategy we have learned. For an object to be completely at rest, two conditions must be met. First, the net external force acting on it must be 0, which ensures there is no translational acceleration. Second, the net external torque about any axis must also be 0, which prevents any rotational acceleration. When calculating the torque due to gravity, we treat the object's entire weight as acting at a single point, its center of gravity. The most powerful technique for solving these problems involves choosing your axis of rotation wisely. By placing the axis at a point where an unknown or unwanted force is applied, that force has a lever arm of 0. Consequently, it produces 0 torque and drops out of the torque equation, which can dramatically simplify the calculations. Therefore, always choose your axis to eliminate as many unknown forces from the torque equation as possible. To wrap up, let us apply our understanding of static equilibrium to the two examples we have discussed. First, consider the ladder. If a person climbs halfway up, does the minimum safe angle increase or decrease? When the person is on the ladder, their weight creates an additional torque that tends to make the ladder slip. To counteract this, the static friction force from the ground must be larger. For the ladder to be stable under this increased tendency to slip, it must be placed at a steeper, larger angle. Therefore, the minimum safe angle must increase. Now, think about the beam supported by a cable. If the person walks outward, away from the wall, how do the tension T and the reaction force R change? As the person moves outward, their lever arm with respect to the pin support increases. This creates a larger torque. To keep the beam from rotating, the cable must provide a larger counter torque, which means the tension T must increase. Because the net force must still be 0, the reaction force R from the pin must also change to balance the new, larger tension.